Welcome back to our physics review. This is for high school physics, and this is chapter 6, which for those of you who don't have the book, it is on systems, work, and energy. These are the very first problems. Now this one, I've changed it a little from the book, all of them from the book, so they're not exactly the same, but they're pretty close. In this case, Ratman, of course, he weighs 70 kilograms. He's dangling on the free end of a 16-meter rope, and he's going to try to swing up onto a ledge by getting the rope to 60 degrees. So we're asked how much work is done by the gravitational force. Now, what do we have to do? Well, in this case, we have 3 important steps that we need to keep in mind. First of all, we have to make sure that we have our knowns and unknowns. We have to draw a good diagram, and of course take our steps towards a solution. So our first step, of course, are givens. Now here's one thing that I'm going to tell many students because I suffered in the same way. Okay, which is, while I'm writing the givens here, I will tell you that many times when I was given these problems, I now that I'm old and I know these like the back of my hand, but there was a time when I didn't know anything about what was going on these. Okay, so let me just, now we're going to draw the initial diagram. Here's my point, is even if you think you just don't know anything about what's going on, I always strongly recommend at least get something on the paper. Get to drawing something. Something might be able to click and clue you into where the next step is. This is so important, okay? So in this case, I have the initial diagram, and I even drew him with a little tail. Now, this is our final diagram, which is when he has already swung the rope to 60 degrees from vertical. So here's the ledge. Okay, and like I said, in this case, even if you didn't know, you could be able to draw these diagrams because you were already given these instructions. Okay, so here our 16 is our hypotenuse, and as you notice, our adjacent and our opposite. If you didn't, you can give them whatever letters you want. You're going to see why I did that. So anyway, here's our units. Now, in order to solve for this, though, we have to figure out, the work. And the work, of course, is the force times the distance. But in order to figure out the distance, we need to figure out this adjacent side. And remember how we have the SOHCAHTOA, which means that cosine is adjacent over hypotenuse. And if we solve for adjacent, we get hypotenuse times the cosine of theta. Now our distance traveled is going to be the total distance minus whatever distance we have left. So here we replace A with our h cos theta, and that we know h, and we know that the cosine of 60 degrees, and this one's 1/2. If you don't, you can plug it in a calculator and it will tell you. So this gives us a distance of 8 meters. Now before we try to just multiply them, keep in mind that the force of gravity and the distance are in opposite directions. So whichever direction you want to set your Cartesian coordinates, just remember that one of them is negative and the other one's positive. Now, doing it this way, of course, we will get the correct answer, which is about negative 5,488 joules, or roughly about negative 5.5 kilojoules. Okay, so the work done against gravity, which is the only difference between what it says, is about negative 5.5 kilojoules. So let's go ahead and move on to the next problem. Now in this case, we have a particle subject to a force Fx that varies with position, as shown in the figure below.
We've got 4 questions.
Now what are our givens? Well, our given is the diagram, and the questions, of course, are from 0 to 4, from 4 to 8, and from 8 to 12. And we know that it's asking for work, so let's just write up our equation, which is force times distance. Now,
It's asking from force from 0 to 4.
Now notice that our work looks exactly like area, and that's no coincidence. Work is the integral of the force over the distance. Now when work is very simple, when our charts are really simple, we can just treat them as simple geometric equations. In this case, we treat this as a triangle. We solve it like a triangle to get 10 joules. Now from 4 to 8, you're going to notice that that's just a simple square of 4 and 5. So we solve it as a simple square. And on C, well, it's just a triangle in the other direction, exactly the same as in A. So we, once again, and for D, of course, we just added them all together. So that's one thing that I want you to now focus on here, which is that work is the integral of force over a distance. Like I said, the reason I say this is because, of course, it's going to get a lot more complicated, so you want to keep this in mind, okay? Work is the integral of force over distance. And we're going to see this one more time when we complicate it just a little bit more. Now, if you haven't worked with integrals, we'll talk about it more later. Okay, now in this case, we have a 5 kilogram object that is hanging vertically from a spring, and when we remove the object, the spring is going to contract by 3 centimeters. Now, I drew it so that it looks like it's going backwards. In reality, it doesn't matter. You're going to get the same answer. So we want to get the spring constant, which is K, that's the Hooke's law constant, and we are given the distance traveled, and we have the weight of the object. So all we need now is to go ahead and solve this here. So we have 5 kilograms. Okay, and let's draw the diagram for answer A. And that is, we have exactly the same diagram in pretty much every way. It just looks a little different with the numbers. In this case, though, our 2 kilogram object is only going to move by x. That's what we want to find out. Now, in order to notice how we solve this, we remember that we have our force diagram. So we have the force of gravity, which is mg, and the force of the spring constant, the Hooke's spring constant, and that is kx. So if we set them equal to each other, we're going to get mg equals kx, and since we want to know what x is, and actually in this case we want to know what k is, we have mg and x. So we have 5, 9.8, and we have 0.03. Remember, this is meters. That's going to give us 1633. Now, our units. Units are going to seem kind of freaky, but really you can just solve it by getting the units of every one of these objects here and dividing them exactly the same way you did it for solving this. And that's going to give us kilograms per second squared. So that is the unit for our spring constant. So now let's go over here and answer the actual question A, which is same way, mg equals kx. We have mg and k, and we want x. So this is going to be real simple. All we do is we set 2 times 9.8 over 1633. Here we go, 0.012 meters. So this is about 1.2 centimeters. We now move on to the more interesting part of this problem, and that is to solve for work. But in order to know how to do work, we need to keep in mind, like we said, that work is an area, and more mathematically stated, it is the integral of the force over the distance. Now in this case, of course, we can treat our fx dx as kx dx. If you look over there when we solved it, that's what we did. So our integral, we take out our k, and we're just solving for the integral of x dx. And that's going to give us kx squared over 2. If you've never seen this, just remember the last part, which is kx squared over 2. So we have our k, and we have our x squared, which is 0.012 meters, and over 2, which gives us 11, or 0.117576, or roughly about 0.12 joules. So that's it. Now, the most important thing I really want you to keep in mind with all of these, of course, is how you set it up and you set the diagram. And from there, the actual solution should just slowly start to reveal itself. Even if you've never done this before, at least take a few steps and you might be surprised at how you will figure out the rest. Got any questions? Let me know. Thanks and take care.